Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X researcher and professional physicist, and today I would like to share with you another one of my articles on brown dwarf stars. And this article is entitled "The Evidence for the Presence of at least 3 brown dwarf stars in the vicinity of our Sun." And in this article I discuss the evidence and some of the strongest evidence for the presence of these brown dwarf stars is images detected by the Stereo A spacecraft and provided by SETI, probably unintentionally, on November 16, 2016. And two of these images are shown in Figure 1. Figure 1 images from November 16, 2016, provided by SETI, showing a large elliptically shaped star and a small spherical darker object in front of the star. On the left is a HI2A SREM image from 1809, and on the right is a HI1A visible light image from 2049. The large object appearing in the image is obviously a star, as it has churning plasma and emits light. However, it is much smaller than the Sun and therefore very likely to be a regenerated brown dwarf star. The small darker object that appears in front of the background star is also an object of interest. It is clearly discernible in the SREM image, and since the SREM detector detects charged particles, not light, we conclude this object emits charged particles. The object is also clearly discernible in the right, which is the visible light image, but it is not completely black, which is what we would expect had it been a planet. So if it had been a planet, this object would be completely black, but it's obviously emitting light. Now, an object that emits both charged particles and visible light has to be a star. And since it is so much dimmer and smaller than normal main sequence stars like our Sun, and dimmer than the star behind it, it is extremely likely to also be a brown dwarf star. The best evidence for the existence of another brown dwarf star further away from the Sun is provided by SETI images from 2008. At the time, the baffle was not as prominent as it is today, and particle and light emission was detected by Stereo A's detectors right through the baffle, showing that it was an introduced background artifact and not a real object protruding from the spacecraft, as illustrated in Figure 2 below. As you can see, we have matter emission right through the baffle. So it's actually a background artifact. There is the proton emission. This is the heavy ion emission. HI2A SREM images provided by SETI from September 15, 2008 at 1409 and 1809 UTC. In both images, the blue arrows point to the brown dwarf, which is seen emitting black and white clouds of matter. The red arrows point to the matter emission from the brown dwarf and is detected right through the baffle. The green arrows point to the matter ejection from the brown dwarf in the direction of the Sun. The Sun is to the right over here. The purple arrows point to the heavy ion, probably ionized ion cloud that is filling the solar system. Sorry about that. Let's continue. So the brown dwarf appears in these images in Figure 2, and as I've shown you, it's indicated by the blue arrow. It looks like a white disk, and that would be the ionized gas envelope around the core of the star. And only a star can have this type of particle emission we see in these images, and I have shown that in a previous article I have made a video on. Next we come to the spectral classification, stellar classification diagram, showing where our Sun, a G25 star, is. This is the main sequence branch. Our star is a main sequence star, which means it's undergoing hydrogen fusion. Brown dwarfs appear here. This goes according to spectral type. The largest stars are the O stars, and as we move down along this x-axis, the stars decrease in size and temperature. And as we move along the positive y-axis, we have absolute magnitude or brightness. So the brightest stars would be here. So these are the hypergiants. These are classification O, and we will compare the sizes in figure 4. So figure 3 shows a diagram which demonstrates the different spectral classes in which stars fall into. The brightest stars are usually class O stars, and the dimmest are the class T stars. The brightest stars are stars with the hottest surface temperature, and these usually emit blue light. The class O stars are also the largest stars and often fall in the hypergiant category. As we move down the diagram, the star sizes fall from 1A down to 7. Let's look at that. So this is O, the hypergiants, 1A, supergiants, and then we have bright giants. These are 2, giants 3, subgiants 4, and 5. These would be the main sequence stars. And below that we have the sub-dwarfs, the white dwarfs, or 7, and the brown dwarfs, or down here they are also small. We can think of them as in 7 or even smaller. Figure 4 shows a size comparison between the different large size spectral classes and a main sequence star like our Sun. So we have the hypergiant. These are the largest and brightest blue stars. Below that we have luminous supergiant. This is stellar class 1A. Below that we have a supergiant, and then a bright giant, a subgiant, and finally a main sequence star like our Sun, which is just a little speck in comparison with the hypergiant. Brown dwarfs appear in the diagram. Now, and this is the diagram in figure 3. Now, I believe that there is actually a difference between a brown dwarf and a brown dwarf star. The main difference is that brown dwarf stars have an ionized gas envelope and brown dwarfs have lost it. Thus, brown dwarfs are actually what is left of the core of a brown dwarf star. Now, brown dwarfs may have gas around it, but it's not ionized anymore. So they may actually have a solid core and some gas around it, and it looks like an atmosphere, and it will have striped cloud formations. Also, brown dwarf stars have a high enough magnetic field which allows them to connect magnetically to the Sun, absorb its energy, regenerate, and start operating as a small main sequence star. Brown dwarfs are older and weaker and no longer able to regenerate, but a non-regenerated brown dwarf star and a brown dwarf are similar in terms of size and radiation emitted. And as we can see from the diagram in figure 3, brown dwarfs are classified as M, L, or T stars and are therefore very dim and not expected to be able to emit visible light, but only infrared radiation. Brown dwarfs are also very small, with their size classified as 7 or smaller. In other words, they can be of comparable size to a gas giant planet such as Jupiter. So let's look at that again. Here we are. These are the brown dwarfs. Both brown dwarfs and brown dwarf stars, that is, brown dwarf stars that have not gone through the regeneration process, which these objects seem to be able to go through in the solar system by absorbing energy from the Sun. Now, brown dwarf stars are stars that have basically run out of fuel. I initially thought that all brown dwarf stars were able to eventually convert all their fuel to iron, but I have realized that, of course, we get different cores. They have different cores depending on when they run out of fuel and the initial size they have as main sequence stars. Some are so small that they never get beyond the hydrogen fusion stage, and so eventually start the aging process. And that process starts with these stars going into the red giant phase and then white dwarf phase. Eventually they turn into brown dwarf stars, and if they started this aging process at a stage when they had burned all the hydrogen, and they were not able to go into burning helium. They would end up as helium-4 brown dwarf stars. So brown dwarf star that evolved from a main sequence star that did not go beyond the hydrogen burning stage would have a helium core, and a main sequence star that managed to end with the production of iron through fusion reactions would end up as a brown dwarf star with an iron core. Also, once a star can no longer have fusion reactions, it cools and eventually will no longer be able to emit thermal radiation in the form of visible light photons. The higher the surface temperature of a star, the higher the motion of the ions on the star surface, which collide, causing changes in kinetic energy and acceleration of the ions. When these ions, which are charged particles, accelerate, an electromagnetic wave or photon is generated. Our sun is hot enough to produce visible light photons, as well as ultraviolet and X-ray photons. But a brown dwarf star, if it cannot drain another star, is only able to produce much lower energy infrared photons. A brown dwarf star also has a much lower electrical potential than a main sequence star that is still undergoing fusion reactions, and thus loses the ability to hold on to its outer layers of gas. But when such a low potential star comes close to another higher potential star, such as our sun, there is an electrical and magnetic interaction between the two, and the brown dwarf star gains energy and protons, whilst the higher potential star loses energy and protons. This is what is happening with our sun. The electrical interaction is often in the form of huge plasma discharges. Huge coronal mass ejections have also been observed to happen in the direction of the brown dwarf star, which causes the sun to lose many protons, its primary fuel. The other mechanism through which the sun loses protons is through coronal holes, points on the surface of the sun where the sun's magnetic field connects to the brown dwarf's magnetic field. If a brown dwarf star comes close enough to the sun's surface, it may also be able to cause the sun's surface to be discharged to the point that it goes dark in all wavelengths. And in figure 5 below, we see the sun in 4,500 angstroms or 450 nanometers, and these images are provided by the SDO satellite from August 21st, 2016. And in these two images from 6:30 and 7:29, it's actually the same image, we see that the sun looks like a hemisphere. The reason for that is because the sun has stopped emitting from the lower hemisphere here. In other words, it has gone partially dark at that time. And these images are basically the same because at the time the visible light images were only available every hour on the half hour. I think that has changed since then. And in figure 6, we see images of the sun detected by the SDO satellite in the 19.3 nanometer ultraviolet wavelength. Images on the top and from left to right are from November 23rd, December 7th, December 21st, 2016, and January 4th, 2017. So these are the most recent images. And images on the bottom are from December 1st, December 8th, December 15th, 2015, and January 4th, 2016. So a year earlier. As you can see, the sun looks brighter a year earlier than it does now. Coronal holes covering between 30 and 40% of the sun's visible surface are apparent in the top images. These are the most recent ones, and in the bottom images, the coronal holes cover between 15 and 25% of the sun's visible surface. So the sun is clearly brighter in the bottom images. What does that show? It shows that the sun has weakened since last year. Thus, in a period of a year, the size of the coronal hole seems to have increased and the sun's brightness decreased. And I should mention that the images on the bottom were chosen to reflect the largest coronal holes from that time interval. And in figure 7, we have images of the sun as detected by SDO in the 19.3 nanometer, which is an ultraviolet wavelength, on January 4th of the different years. This is 2012, 2013, 2014, 2015, 2016, and 2017. And if we compare image from the 2012 with the image from 2017, it is quite clear that the size of the coronal hole and the brightness of the sun has decreased. And this would be an indication that the sun's emission of ultraviolet light has decreased in that time. Now, when brown dwarf stars in the solar system, with brown dwarf stars in the solar system, and since brown dwarf stars emit mainly infrared radiation, we expect the infrared radiation detected on Earth to increase. Figure 8 below shows that this has happened. It is a solar irradiance plot at the 897.83 nanometer wavelength. It's between February 25th, 2003 and December 21st, 2016. Now, the infrared wavelength is between 700 nanometers and 1000 nanometers, so this is within the infrared wavelength range. And if we look at the plot, here we are, we see an increase from about 2012. So this is a solar irradiance plot for the 897.83 nanometer infrared wavelength between February 25th, 2003 and December 21st, 2016. The detected infrared radiation goes up from 2012 and shows an increasingly sharper increasing trend between 2012 and the end of 2016. And there we are, increasing infrared radiation impacting the upper atmosphere of the Earth. And in figure 9, we have a solar irradiance plot for the 399.79 nanometer. This is an ultraviolet wavelength, and we show a decrease from about 2014, indicating that the sun is obviously emitting less ultraviolet light, and that agrees with what we have seen in the SDO images. We also have a decrease from 2003, and then there's a slight increase from about 2009, but this increase and never goes up above the 2003 level. And this is what basically say here. So basically ultraviolet radiation, there's a sharp decline in the last 2 years. So in conclusion, the evidence supplied by SETI images, SDO images, and irradiance plots, in other words, irradiance plots show that ultraviolet radiation has decreased, the sun has decreased, but infrared light has increased, and that would be due to brown dwarf stars being in the solar system, since especially when they first come in, they mainly emit infrared radiation. So again, in conclusion, all of these show that we indeed have brown dwarf stars in the solar system. In fact, the evidence, when put together from all of these SETI images, SDO images, and irradiance plot, is overwhelming. This is Dr. Claudia Albers, Planet X physicist.